Okay, so we decided that we make the lecture like this, put it in record, and then everybody can see it. Okay, so what is a subobject? So we already discussed the notion of monomorphism or one-to-one map, and yes, you remember that it means that it induces one-to-one map between this home and this home, and basically a subobject you can think of it as an object X and a morphism between and the monomorphism between X to Y. But usually when we think about subobjects, we can think about them as is and not only up to isomorphism. Yeah, so we can ask whether two subsets in the same sets are the same. Yes, it's not very meaningful to ask whether two abstract sets are the same because it depends. We can often find some natural bijections between different sets, but we will consider them as the same. But subsets are either equal or not equal. So, and here what we can do is like a straightforward trick. So we can define sub-objects of Y, like the collection of all pairs X and phi, where phi from X to Y monomorphism, modulo the equivalence relation, which is given just by isomorphism in the over category. Yeah, so this subset is subset of objects in the over category, so and modulo equivalence relation. So usually it's not that good idea to take take a okay. Okay. At some point the connection was lost. Only I have disconnected or all of you disconnected too?
Only you.
It happened
Only
in
okay.
Weizmann, I think.
Rami is start so I started screen sharing, but you don't see anything, yes? You don't see my screen, do you?
No.
And the good thing is the Okay, now you see me? Do you see and hear me?
I hear you, but
Diamond record. Okay, I'm really sorry. The internet in my office stopped working. Now, do you hear me?
Yes.
Yes.
Okay, so with small and unreasonable late, how? Oh, half an hour late. Oh my god, 50 minutes late. Not that bad. So let's start to continue. Try to continue. So, where did I stop? What was the last moment you heard? Anybody? Do you
Maybe
hear
if you
me?
repeat the last line anyway,
Okay.
if any.
So we define sub-objects, a set of sub-objects in Y in the following way. We consider pairs of object X and monomorphism phi from X to Y, and we take this set up to the equivalence relation, which is given by isomorphism in the over category. So this set is subset of the set of objects of the over category because it maps to Y, and we consider up to the equivalence relation given by isomorphisms. So in general, taking isomorphism classes in category. So if it's every category, you can consider all objects up to isomorphism. And in general, this is not okay. It may be a good idea, but it's you lose lots of information. You can't reconstruct the category from the set of isomorphism classes. But in this case, it's not so bad, because in this case, basically, if we have two objects, x and x prime, either there is, so the set of morphism between them is either singleton or empty set. So the number of morphism is not more than one. And it's rather easy to check from the definition of monomorphism. Here maybe it's an exercise. So yeah, so if those two guys are monomorphisms, so here we have uniqueness. So not necessarily existence, but uniqueness. Oh, okay. Somebody have the microphone. Oh no, now it's okay. I still hearing echo. Maybe it's my microphone.
Sorry, I mute now.
Okay, good. Thank you. So you see the screen that I'm sharing. Okay, never mind. Yeah. So the set of either.
Yes, we see.
Thank you. So the set of maps is either so the not necessarily the it's not necessary that there is a map between x and x prime in the over category, but if there is such map, then it is unique. And this means that now when we consider the set of isomorphism classes, what we left, like from the structure of the category, we left just with a poset. We will say that x prime is a sub-object in x if both, okay, maybe it's not good. Yeah, so let x and x prime be sub-objects in Y. So sub-objects in Y, just isomorphism classes of pairs of objects with a monomorphism. So we say that x is smaller than x prime, or just sub-object in x prime, if and only if this definition there is phi or psi maybe from x to x prime in the over category. So exercise that in this case psi is monomorphism, and as I said before, in this case psi is unique. So basically, the entire structure of the category is encoded in this poset, in the collection of sub-objects, and the order relation is given by this
The
by this definition.
how do you call this category? The over category or
No,
the
so I
because
have the over category, but the collection of sub objects is a subset of objects in the over category. I can consider it as a subcategory, but instead, what I do usually, I consider a set of equivalence classes and consider it as a poset. And in this case, I kind of don't lose information. So the collection of sub objects in the category is you can think of it as a process and you will not lose information. So what it means formally we'll discuss maybe in a couple of hours, but for now it's a definition. So I just defined a poset of sub-objects. Poset, you know what it is, yes, partially ordered set.
can you just repeat on the equivalence
This
relation?
equivalence,
Yes.
this equivalence is isomorphism in the over category. So you remember the definition of over category and you remember the definition of isomorphism, so this is equivalence. And this is the order relation.
So this is not in the over you wrote just in the definition in the over category. Did you mean
Yeah,
the
here
sub?
yeah, also like this, yes.
But you said in the definition there is psi in the over
In the over
category.
category of y, yes. Yes, so I consider the collection of sub-objects. If I want to consider that a category, it will be full subcategory of the over category. But then I pass to equivalence classes, yes. So, oops, sorry. What happens? Yes. So I consider the collection of sub-objects just as a set with an order relation, and which give me a category, but it's something more concrete than just abstract category.
So this is in the sub category, not in the.
It's the
Right?
same. Okay, I
Okay.
don't consider category of sub-object. I could have do it. Category of sub-object would be a full subcategory of the over category, just all the monomorphisms. But when I usually say sub-objects, I don't mean objects in this category. I mean isomorphism classes in this category, which is basically information-wise the same, but of course it's different things, yes. And therefore, about sub-objects, I can ask whether they're equal or not. And objects in category, I usually don't ask whether they're equal or not, but only whether they're isomorphic or not. But in this case, since if you have a morphism between two sub-objects, then it's unique, so it makes sense to ask whether they're equal or not. And of course, you can check that in all the cases that you know, like sets, topological spaces, modules over an algebra, vector spaces, whatever, sub-objects corresponds to what you know as sub-objects. Okay, so this was the first thing. So now I left my notes in the office, but I will open them here. And we'll see. I did not. Okay, the next thing that I wanted to say before and forgot about it was filtered limits, filtered colimits, etc. So you remember that we talked about limit over a diagram in general, yes? So if we have a poset, and so diagram have its shape. The shape of a diagram is a graph, yes? So if we have a poset x, we can make out of it a graph, I don't know, gamma x. So just vertices as elements in x, and they draw an edge each time x less than y. And then I can consider commutative diagrams of this shape. So if I have a poset, I will just say, if I have a poset x, I will say commutative diagram of shape x, and will mean just the commutative diagram corresponding to this of shape of the graph corresponding to x. So now a poset is called filtered. That's a definition.
What is the graph? Just can you remind us?
I just say that the vertices of the graph are the objects of the elements in set X, and they draw an edge between X and Y. A directed graph, so I draw a directed edge between X and Y if and only if, say, X is less than Y, less than or equal to Y.
Okay, thank you.
So, definition, a poset is called filtered if for any poset x and y in capital X, there exists z in capital X such that x and y are both smaller than z. Yeah, so it's something slightly weaker than well ordered than full order, but for many practical space cases, it's almost as good as full order. So filtered limit is limit over a commutative diagram whose shape is a filtered poset. Why I'm talking about it? Because they somehow behave nicer than general limits. They are very similar to limits over sequences. So in fact, if you have poset which is countable, so filtered poset which is countable, so of course it doesn't have to look like this. It doesn't have to be like full ordered and like I don't know how to call it, omega 0, like the standard, the most simple poset, like natural numbers. It can have things like this, for example. Yes, you can have such an order. So kind of like a tree. But it doesn't really matter. So each time you have a poset like this, you can replace it by a subposet, which will look like the natural numbers, and which will, am I right? Yeah, I think if it's countable, I'm right. So you can replace it by a subposet that will include all this information. So meaning that the limits will be the same. I'm not 100% sure that I'm right for countable posets, but I'm pretty much sure. And anyhow, the limits over such posets will behave like limits over just sequences. And many theorems that will be true for limits over sequences will be true for limits over general posets, over filtered posets, but will not be true for general limits or limits, even finite limits, but not over posets. And okay, so this is one reason why they are important. And another reason is that, okay, so if you want to talk about finite limits, then you know how to do it. So you know that you basically have, say, Fourier product or equalizer or something like this. And once you have equalizers, you can build from it any finite limit. But you cannot build from it infinite limit, or at least you cannot do it with finite procedure. So we say that you can do with products and with equalizers, you can do everything if you have infinite products. But another way is to talk, so infinite products are not filtered limit. Yeah, so, or even finite products are limits, but they are not filtered limits. So if you want to talk about, but you can do it with filtered limits. So if you have finite products or finite limits and filtered limits, then you have all of the limits. And the reason, so maybe exercise, if C have finite limits and filtered limits, then C have arbitrary, or just have limits. And the hint is very simple. If you have a diagram you can consider all its finite subdiagrams. It's a big collection, and this collection is filtered. So let me say the hint. So if we have a diagram D, let D be a diagram, let FD be the collection of finite subdiagrams of D. Yes, so you can consider this if you have diagram of of this shape. So finite subdiagrams, okay, there are of course many of them, but the most interesting for us will be finite subsequences. But you can do it with any diagram and consider all finite subdiagrams. And finite subdiagrams have a natural structure of a poset. So a diagram can be inside another larger diagram. So we'll say it's smaller or included in a larger diagram. So the claim is that the limit over D is the same like the limit over FD, or let's call it, I don't know, F in FD of limit. So like let's write it like this: limit of limit over F or X in F. So you can take limit over each finite diagram, and then take the limit over all the poset of all subdiagrams. So yeah, so this is very standard in category theory, and probably not only like in set theory. So you just run over each finite subset. So yeah, you can exhaust any set by its finite subsets. Yes, any set is union of its finite subsets. So and the union of finite subset is kind of ascending union. It's filtered union because each time you have two finite subset, you have their union, which is larger than both. So you can divide all the problems to problems which are finite and problems which are like ascending, which is the intuition that we have behind filtered limits.
Rami, so the definition of filtered, I think, should be not only for two objects. For any set of objects, there is someone that block them.
Not any set. Okay, I'm not sure, but you cannot take just all of them. Yes, this will be too much to ask. Maybe any finite set, but then it's automatically from any two. Okay, it can be my homework. So what I remember was any two objects, but
No, but I'll just say just so the limit. So okay, just what would block all of the limit from outside? Okay.
So the limit is not necessarily, yeah, if a poset have a maximum, then a limit over this set. By the way, I'm talking about limit, and I probably should talk about co-limit in this diagram, in this picture. Oh, I'm sorry. Okay. So let's say everything was for co-limits, like direct limits. So of course, everything can be stated dually, and then you just consider the same poset, but with opposite. Instead of objects that larger than both, you can consider objects that smaller than both, and then you can take limits. Or you just take different, so each poset give me a category, but by drawing an arrow from small element to a big one, but I could have done it the opposite way. So yeah, I don't know what to do with it. So let me say finite. Yeah, of course, this is also true for limits, but just the definition of filtered limit is different than what I said. So filtered column. Already. This was monomorphism. Let now poset called filtered if and only if this. Yes, so I didn't say what, okay, I didn't write it, but I said it. So a filtered co-limit is a filtered over, is a limit over a filtered poset. Now a filtered limit is everything the same but opposite, yes, so I need to reverse the order in my poset when I do it. Or change the definition of filtered, yes, so. Okay, Tal, you still have a question?
Yes, maybe I should investigate, but I just didn't see saw the solution. If not, find it. But yes, I will work about this.
Okay, the solution for the exercise, yes?
Yes.
Okay, so I just wanted to say the hint that, and this is very common idea in many things, I think, set theory and category theory, that you often can divide with the problems from like finite problems and ordered problems. And maybe the simplest example is within a set. Like you have a set, which is of course union of all the singletons in it, but this will be somehow completely disordered union. But it's also a union of all its finite subsets, which looks like obvious statement, but the collection of all its finite subsets is ordered. It's partially ordered set, and it's ordered rather nicely. It's filtered it's filtered partially ordered set. So yes, yeah. So this obvious observation that if that any set is a union of all its finite subset is useful. Okay, let me see what is the next topic I wanted to recall. Should say last time. The notion of extension. Yeah, it's a very nice notion in abelian categories. Oops. So in abelian category, we have the notion of exact sequence. So definition, let C be an abelian category, X, Y, Z is exact sequence if image phi is equal to kernel psi. So when I write here equal, I can mean just isomorphic in the over category of Y because they're both maps to Y, but in fact they're both sub-objects in Y, so I can think about image phi as a sub-object in Y and the kernel psi as a sub-object in Z. So, so yes, I call the sequence exact if I have such an inequality. Is it clear? Okay. So, and of course I can use the same definition if I have a longer sequence. So a long exact sequence is exact if it's exact in any point. And now, oops, sorry. So now definition, we say that A is an extension of B and C if we have exact sequence 0, B, A, C, 0. Okay, so I believe you also saw such sequences before? For somebody the first time? No, good. So yeah, so this is called short exact sequence. And when you see such sequence, it always means that the first map is embedding because it has 0 kernel. And the second map is onto because its image is everything. And since we say that the image of this map is equal to the kernel of this map, it basically means that B is a sub-object in A, and C is a quotient on A of A, and quotient exactly by B. So it means that we can kind of think about A. So this is called extension. Yes, so A can be glued, somehow build up from B and C. Yes, of course, it doesn't mean that it is the direct sum or direct product of B and C, but they are extending each other. So you probably saw example of such in abelian groups and vector spaces, of course. Yes, so this is called extensions. And we have many so you know many examples of extensions. So maybe one of the basic statements in linear algebra is that there are no non-trivial examples of extensions. So each time we have an extension, it's in fact a direct sum. Maybe not in a canonical way, but it's a direct sum. And maybe the first surprising fact in commutative algebra that it's not always true. So even for abelian groups, so for me it was a surprise that you can have an extension Z maps by doubling it to another Z, and the quotient is Z modulo 2. But in any way, Z is not the direct sum of Z and Z modulo 2. It can't work. So this is example.
So an extension is coming with new arrows, right?
Yeah, so when you say that A is extension of B and C, we usually imply also that we have some fixed arrows. Fixed short exact sequence. Yes, the same object can be extension of two different objects in some different ways, of course. Okay. And this gives rise to the notion of the goth in the group of a category. So definition, if, let A be an abelian category. Now I want to define the goth in the group. So the idea is that I want to take all the objects and more or less say that those will be the element of the group. And each time one object is extension of two, I will say that it is a sum of those two. And now you can make out of the definition in several ways, but maybe if we're in category theory, let's make it in a categorical way. So let's define first of all, I don't know, okay. Okay, it's added notion, nice map from object of A to abelian group gamma group is a map such that, so I will probably give too much axioms. 1, 0 maps to 0. 2, if A is isomorphic to, to A prime, let's call it phi. Phi of A is equal to A prime. And 3, if we have exact sequence like this. So each time you see a sequence, a short sequence like this, and if nothing says that, usually this sequence is exact. So if this is exact, then phi of B equal to phi of A plus phi of C.
Just nitpicking, you need to write phi before the A prime at stage 2.
Okay, so the collection of all pairs gamma phi from A to gamma, and gamma is good. Oh, sorry, phi is good. Or nice, I said, yes. Phi is nice. So this collection is certainly a category, because once you have a nice map and you compose it with a group homomorphism, you get a nice map. So you can take the initial object here, and this is defined to be the Gottlieb group of C. Sorry, I say A, so
Rami, is it necessary to claim 2, to demand 2?
No, probably many of the
I
things
think
are
that
not
the 3
necessary.
is implying this. If
I
you
think
take C
3
equals
and
0.
1, yeah, so I think 3 and 1 implying this, so you probably need to demand either 2 or 1, but maybe you can avoid even both of them, I'm not sure. So I think 3 and 2
Yes.
imply 1, 3 and 1 implying 2, so you can erase at least one of them and maybe both.
In case of C equals 0, I mean, of course. Okay. Yes. So that's all.
Yeah, so I wrote both of them because I didn't know who of them I like less, so but you can erase one of them and maybe you can erase both of them if you think a little bit more. Yeah, I didn't prepare this point. I somehow forgot that there is some subtlety here. Okay, so some nice exercise to compute K of A. Compute for different A. Maybe the best two examples are vector spaces and fine dimensional vector spaces. So any of you have guesses what goes in the group is larger, vector spaces or fine dimensional vector spaces?
For finite dimensional, I suppose it is Z.
Exactly. And for vector spaces? No guesses? Yeah, so the spoiler is that for vector spaces it is 0. It is 0. It's kind of surprising, but we basically can swallow up any vector space inside the larger vector space, and the larger vector space will not even fill it. So, okay, it's a nice exercise. And for fine vector spaces, very intuitively. So basically, the only thing that survives is a dimension. So isomorphism class of fine dimensional vector spaces are natural numbers, but since you want to get a group and not a semi-group, then you have also to get negative numbers. So it will give you into exactly will give you yes.
Is there a natural example where the map into the Grothendieck group is surjective?
Naturally, yes, but smart, I'm not sure. So, okay, maybe in case of vector spaces. In any case, the answer is 0, and you have this, it works. So, and in many cases, the answer is 0, but they're not that interesting. In other cases,
is subjective.
From objects, I think you meant from objects to Gottlieb group. Yes.
So
You
it's
tell me
not
this
Yeah.
what you mean? For vector spaces, I think it is.
No, because you have the minus.
Not for fine dimensional vector spaces, for vector spaces.
For vector space, it's subjective.
Yeah.
Yes.
So in any case, since the right hand side is 0, then any map to there is subjective. And there are many natural examples like this. So the stupid answer is yes. But the smart answer is probably almost never, because if you want that the right hand side, if you want something meaningful, then it usually will not work. Yes. So you usually don't have negatives in your category, but you probably can find an artificial example where it is not 0, and natural probably where it is so not zero and subjective. And nature examples, I don't know any of that.
I don't think you can.
You don't even think they can find an artificial example?
Because zero is not an extension of anything. Somehow.
Really, I cannot kill. No, you're right. Zero can't be extension of anything.
So,
So very
there
simple.
might be
Yes,
some examples, but I
no,
mean,
you're right. Zero. If zero is extension of two objects, then each of these objects is isomorphic to zero. Yes.
yes.
So if I want, so if I want that those object will not represent zero in the Gaussian group, then I cannot do it. So probably it's never subjective unless the right hand side is zero. And maybe some exercise that it was implied but I didn't say it is that the Gaussian group always exists because it now just defined it as initial object in some category. So it's not automatic that it exists, but it does exist, and there is very simple, straightforward construction. So exercise 2 go through it. Any questions? No questions? Okay, so I think we deserve 10 minutes break, and then we'll get back to what I actually intended to tell this time.
I have a question for the break because it's not in the material yet. We didn't discuss about functors, so my
This is the
question
next
is
topic, by the way.
what?
But okay, this is the next topic. This is what I will do after the break.
Okay,
But okay.
but what I wanted to ask, whether this Grothendieck group respect functors, like
Yes.
in a covariant way or contravariant?
Yes, in
Exact
covariant.
functors.
Okay.
Yes, I'm sorry, guys, right. Yes, if you have a exact functor between two categories, then it induces.
Probably it's fine
How-
also. I mean, it doesn't have to be completely. I mean, right exact is probably also enough.
Right,
It's
exactly enough.
general
But
law.
if it doesn't map,
Because you can talk about the K-fear of the derived category.
no, but this category not. It's different answer, no? You say if it's right exact, then
No,
it
if you're
works.
talking about perfect complexes, then it's the same basically by definition. I
But
mean, you
how
don't
it
talk
actually
about all the
works.
derived category. Talk about the.
No, but how it actually works. So I have an object. I will map it.
I mean, let me restate. For an exact functor, it just in the natural way respects the Grothendieck group. For a non-exact functor, you have. I mean, you don't just define it as an object goes to f of that object. It goes to something else more complicated, but it's still defined. But you can still define.
You can correct the definition, so it will.
You can correct the definition to some Euler characteristic thing.
I see. So the Grothendieck group will be the same definition, but you will correct the induced map between the Grothendieck group will not be the naive one because it will not respect like the. Okay, so you can define it in some complicated way, and if it's right exact or if it's left exact, but if it's not exact at all, then you're in trouble.
It might be complicated. Yes.
But from the derived Grothendieck groups, you do have always.
For derived, you just exactness in the derived sense.
Yes. Okay. Yes, which is also not automatic, but yes. Okay. Okay. So
Also, Rami, I have a nitpick. Did you define filtered? Did you define filtered categories or filtered diagrams?
Filtered diagrams by basing it on filtered posets.
Yes, so it's very much a nitpick, but technically this is called directed diagrams, and filtered is the generalization to categories.
Oh, good.
It's not important at all.
Yeah, I never. So I heard the notion directed, but then I started to hear more the notion filtered, so I never understood why. So this probably is the reason.
Yes. And filter is usually for colimits, and co-filter is for limits.
Okay, so I said that filter. I start with saying that filter is for limits, and then I said that I was wrong, and it should be co-limits. Yeah. But you said that
just
when I talk about
it's not something that I remember personally.
Yes, indeed. Co-filtered, so it's the opposite condition on the square set, yes?
Yes.
Okay, very good. So we still have 7 minutes left for the break. So I want to drink something. See you. And so I'm leaving you the room. And Okay. We can wait another minute. Any questions before we start? Okay. So everybody is back from the break? Guys back? Tal, are you back? Not back. Yotam, are you back? Not back. Okay, so we'll wait another 2 minutes.
While we're waiting, can you recommend some reading material that follows the course?
I'm not really good at it, but I put on a website the McLean book, which is supposed to be good, but maybe it's a bit too heavy. So the course is not like follow any specific textbook, so the order will be different probably in many textbooks. There is some book which is specially devoted to abelian categories, but this is, yeah, I don't remember its name. But I think best in this case will be like NLab or something like this, maybe again a bit too heavy, but
NAB is not much of a book. It's
yeah, it's
literally
not
an
a book.
encyclopedia.
Yes, but for category theory, you don't think it's good?
I don't know. I mean, you can get very easily into a rabbit hole where you just try to read a definition and it references another definition, which references another definition.
Even when you like do, I don't know, exact functor, yes?
Definitely. I mean, I think if you do an exact functor, it might give you also a much more general version.
So okay, maybe bad example. Maybe bad thing, yes. So,
Let's
but I
see.
somehow have a feeling that category theory is something which is very well like documented in the internet. But maybe I'm wrong.
Sure, maybe
Yeah, so
like a
for-
summary, like notes from previous years.
Ah. Yeah, we didn't do anything in notes last time, exactly before I had the feeling that we don't really need them, which maybe was wrong. And guys, do you have any suggestions?
I don't personally know this book, but I know that Vakil's book on algebraic geometry starts with category theory. I don't know if it's a good general category theory.
Yeah, so I heard very good things about Vakil's book on algebraic geometry.
Yeah, but it might be also just be good as a start for category theory, not for general category for algebraic geometry.
Like it. Yeah, so maybe it's a good idea to start from there. Yeah, you have to have like also abelian categories, so you do it as some logical algebra, yes. So
yeah.
okay, maybe it's good.
But it's short.
Short, it's good.
I think.
Okay. And you can ask probably the previous TAs. So the previous, okay, they're all in the website.
I mean, for example, it doesn't seem like he talks about general limits, only the limits that he kind of wants.
which are sequences, yes.
No,
And yeah, and of course,
Firebird. No, he talks
yeah.
about limits and constraints. He has a chapter. It's near the end. Or in the middle. I don't know.
Okay. So I think now we certainly should continue. Everybody is back from the break? If somebody is back, can he show it?
Yes.
Yeah, I see. Okay, so I see at least there is a
Uh,
critical
Yes.
mass. Okay, so we have a critical mass, so we can continue. Where we are, functors. Okay, so basically one of the ideas in category theory is that each time we have some mathematical objects, and we have to talk about legitimate map between those two objects. So for groups, we have morphisms. For vector spaces, we have also linear maps. And for topological spaces, we have continuous maps. So of course, you can ask what will be the legitimate maps for categories. And the answer is functors. So if I have C and D, two categories, let C, D be categories, and phi. So a functor f from C to D is the following data, which of course by abuse of notation will use the same name. So it's the following data is f from objects of C to objects of D, and for any x in C, a map. So x and y in C, a map, let's call it fxy, from more x to more, so xy to more f of x, f of y. So in other words, it's something that acts on object, that map object to an object, and map morphism to morphism, and in ways that, of course, morphism between objects to morphism between two corresponding objects. And of course, we want it to behave nicely, namely to respect the composition, such that, or maybe, okay, let's write all of the things again. Maybe many of them are not necessary. F of identity x is identity f of x. So to map identity to the corresponding identity, and f of phi composition psi. I write phi composition phi, so it implies that phi and psi are two maps which are composable, meaning that the target of phi is, or sorry, of psi is the source of phi. Is f of phi, f of psi. So this is the notion of functor. Sometimes it's also called covariant functor. And there is a notion of contravariant functor, which is basically the same idea, but it's instead of preserving the direction of the arrows, it's reversing the direction of the arrows. So I think like modern approach, you don't discuss contravariant, like separately covariant and contravariant. You discuss functors, which are always assumed to be covariant. And when you want to talk about contravariant functors, you just say it's a covariant functor forms the opposite category. So since you have this idea of opposite category, you don't really need to say everything twice. So this is true. So is the definition of functor clear?
Yes.
Okay, so it's very tempting at this point to say that functors, that categories, the collection of all categories form a category. And it is correct in a sense, so you can consider objects to be categories and morphisms to be functors. And as I said before, there's two problems with it. One which is rather technical, the size. Categories are kind of too large to form a set, but you can do it, so you can consider the collection of all of them. But this is something negotiable. And there is something which is not that negotiable, is that it's not what we want, because functors are also somehow just, so we don't want to think of the collection of functors between two categories as a set. Not only because of its size, the size can be fixed, but because we don't want to consider equality of functors. So maybe I will start with defining the category of functors. So this is a category. The category of all categories is not a good example of category, but category of functors, so between two categories, is very nice category. Funct CD. So what is the category of functors? So the objects here are going to be just a collection of all functors. CD, like functors. And what is morphism between two functors? So I need to define more between f and g. Yes, so it's also called natural transformation. So people so its original name was natural transformation, and people, I think, for the algebraic topology still use mainly this name. I don't really like this name, so I prefer to. So this name implies that there are some notion of transformation between functors, and then inside it some nicer transformation which are called natural. So I don't really know any other notion of transformation between functors. The collection of all functors form a category, and in that category you just have morphism. So I prefer to use just morphism between two functors, because the word natural mean many different things in mathematics. So like we say before, canonical, natural, they mean more or less the same. And of course, not any morphism between two functors is somehow canonical, although it is some indication that you're doing something. So if you have morphism between two objects, which come from morphism between two functors, then it is some indication that it is more natural than others. But it's not always the case. So let's define what is morphism between functor. So phi, for definition, phi from f to g, or a morphism phi from f to g is the following data, is an assignment, for any x, you want to assign phi x from f of x to g of x. Yeah, it makes sense. You have so for any, you want to map between f and g, so it like maps on the value, map between f of x to g of x. So this is the data, and now you need to specify the conditions such that, and then you write the most natural thing you can do. So the functor also do something on maps. So you start with two objects, x and y, and map phi between them. And now you have f of x and f of y, and the map f, we'll call it fxy, but usually we'll just call it f of phi between them. And you have also vertical maps. Phi was bad. Okay, maybe phi is good, but this phi is bad. The vertical maps, we call them phi x and phi y. So of course, when we see a diagram, the natural thing to demand, such that this diagram is commutative. So this is a definition of morphism between functors. Is it clear? Okay. So this basically gives us indications that the collection for category should not be considered just as a category. You can consider it as a category, but you lose some interesting structure here, because what happened here? No. Yeah, so morphism between, so the collection of functors between two categories form a category, and then the collection of morphism between two functors form a set. And of course, so when you see two functors, the more natural question to ask not whether or not they're equal, but whether or not they're isomorphic. And this gives us the notion of equivalence of categories. So definition. F from C to D is called equivalence if and only if there exists G from D to C such that, so we can first perform F and then perform G. So we get a morphism between a functor from C to C, but we don't want it to be equal to identity functor, but we want it to be isomorphic to identity functor. And so you remember, no, I need to say what is an identity functor. It's just identity on the object, object's identity on the morphisms. And similarly, first perform G and then perform F. So this is identity on D, maybe, sorry, on C. And this is identity on D. Note here that something, yes, there is something confusing, that when we talk about equivalence, we want just the functor, one of the functors, to be the equivalence. We don't really want to remember what is the inverse functor and what are the isomorphisms. This is rare in category theory. Usually in category theory, each time that something exists, you want to fix it. But when you talk about equivalence, you don't want to do it. And this is something very general in higher category theory, that you always want to make your definitions in such a way that to state that something is an equivalence will not be to give an additional structure, but just to be a property. And maybe some drawback of category theory is that, like of classical category theory, and I think it's more or less fixed in the more modern approach, that the fact that something is that, like, the natural thing to do here looks like as if it put some additional structure, that to be equivalence is not only a fact but an additional structure. But it's like experience shows that it's not a good idea. So although it's looks more natural in this case, and in fact you can try to change the definition of a category in such a way that you will not need to choose anything in order to make something an equivalence. But this will make it very heavy, so we don't really want it at this point.
When you mean the equivalence in the isomorphism, you mean in the category of functors?
These isomorphisms, yes, are in the category of functors.
The natural transformation in the
natural transformation, which are invertible as natural transformations.
Okay.
Yes. So there's also a notion of isomorphism of categories. Yes, this was a notion of equivalence of categories. There is some notion of isomorphism of categories. It's not a good notion. Again, I will not say never use it, but remember that you can use it more or less only like internal notion when you want to define something in category theory, like very basic in category theory. You can use it, and sometimes probably there is no choice, like equality of objects. You can talk about equality of objects, but you don't need to do it outside the most basic definitions. And here the same. So you can talk about isomorphism of categories, that the two compositions are equal to identity. And this is very rare in practice. So you will consider two categories as if they were the same, if they are equivalent. Although they often will not be isomorphic. So let's do maybe some examples of functors and of equivalences. So maybe for example, say, I want to say two nice notions. So in sets, we have the notion of bijection, which is like the notion of equivalence here. And we have the notion of one-to-one and notion of onto. And together they kind of give the notion of bijection. And we saw that the notion of one-to-one and notion of onto can be extended in not in more than one way, but yet to any category. But now we talk about categories as a collection, which, as I say, it's not a good idea to think about it as a category. So we have a notion of equivalence as the analog of bijection or of isomorphism. But what about one-to-one and onto? So the surprise is that there are three notions, because we like went one level up in the categorical level. We have more than not just two notions, but three notions. So functor can be faithful, can be full, and can be essentially surjective. And if it's both faithful and full, it's called fully faithful. So faithful should be thought of as the like most analog of one-to-one. Essentially surjective is like the size of onto, and full is something in the middle. So definition: f from C to D is faithful if it is one-to-one on more. So if for each two objects, it induces a one-to-one map on morphisms. 2 is, or maybe I will put the one here. Is full if it is onto on objects. Oh, sorry, not on objects, on more. So this is usually not used by itself. So usually the notion that we will use will be fully faithful, fully faithful mean full and faithful. So this very common notion of functor which is fully faithful, which is both, so which is bijection on morphisms. Isomorphism, but on the level of morphisms. By the way, this gives automatically, this is very simple exercise, that this functor is one-to-one on the level of isomorphism classes. So it's not really makes sense to ask a functor to be one-to-one on the level of objects, because objects are not supposed to be equal or not equal. So even equivalence can be not one-to-one on the level of objects. You can easily find example. But a fully faithful functor is always one-to-one of the level of isomorphism classes. And essentially surjective is onto on the level of isomorphism classes. So again, doesn't really make sense to ask a functor to be onto, because maybe even if it's an equivalence, the other category might have more objects which are isomorphic to objects that come from the first category. But it does make sense to ask it to be onto on the level of isomorphism classes. So maybe some exercise about it. So what did I say? Yes, it's fully, the thing that I said just, fully faithful implies one-to-one on objects. It does not work for the other way around, so you can find counterexample. Find equivalence which is not one-to-one nor surjective on objects. Okay, this is, we'll do some examples and then this will become an easy exercise. What other example or what other questions you want? Yeah, okay, maybe now is the time to state the main theorem in this subject, that fully faithful and essentially surjective is an equivalence. Fully faithful and essentially surjective implies equivalence. And exercise the other way around. Yeah, so equivalence, of course, it's both fully faithful and essentially surjective, and the statement, there is a theorem for the other definition. We will not prove this theorem. It's also can be considered an exercise, but with a star. It uses the axiom of choice, which makes the proof a little bit ugly, but basically straightforward. Okay, so now let's do some examples. Okay, I had in the notes examples written.
But essentially, surjective does not imply surjective. Full.
No. You can
Oh,
find
the other way. The other way. Full is not essentially surjective.
no. Full is only full means surjective on the level of isomorphism classes. Sorry, on the level of morphisms. And essentially surjective means surjective on the level of isomorphism classes.
Why does it is not imply that if you are surjective on this, you would be surjective on the isomorphism class?
Okay, it's very easy to find artificial examples. So you just isomorphism classes. So on the level of morphism between two, maybe I should say it more.
Just take a category and its subcategory. The inclusion is always fully faithful, but I mean, it definitely doesn't have to
Usually
be
not
subjective.
essentially surjective. So maybe I need to say, what do I mean onto on the level of more? I don't mean on the level of more from all objects to all objects. I mean from more xy to more f of x, f of y.
Okay. And in surjective, what do you demand the equivalence will be?
Essentially surjective here.
Yes.
It should be onto on the level of isomorphism classes. So the objects themselves, you have to be able to reach each object. Of objects, yes. You have to reach every object up to isomorphism.
Great, thank you.
Okay. So, yes, the corollary of this theorem, or maybe I should write it, corollary, if f from C to D is fully faithful, then it is equivalence to its essential image. What do I mean by essential image? I basically take the image on the level of objects, but take everything that's isomorphic to those objects. So I can think about fully faithful example, fully faithful functors as an embeddings. So basically there is subcategory, full subcategory in the target, such that the map become an embedding. And there is something similar to just faithful. If f is just faithful, then okay, I cannot actually think about f as any. Okay, then it's not just, it can be not one-to-one objects, for example, or something like this. But you can basically replace C by an equivalent category C prime, D by an equivalent category D prime, and F by a functor. Okay, maybe I write like this. And C prime will be a subcategory of D prime, not necessarily full. And yes, and this diagram will be commutative, or in fact commutative up to isomorphisms. So it means that after replacing C and D by some equivalent categories, you can think about C as a subcategory of D and your functor just as a standard embedding. And this goes back to the first lecture when I was saying some things which didn't make sense back then, like that metric spaces is a subcategory of topological spaces. So of course it's wrong. Metric spaces are not subcategory of topological spaces. But I can replace a category of topological spaces with another category such that metric spaces will become a subcategory of that other category, and nothing will change up to equivalences. So in this case, what you actually do, let's talk about metrizable topological spaces. So you can talk about metrizable topological spaces, and you can talk about metric spaces when you don't care about the metric. So the objects are metric spaces, and morphisms are just continuous map. So I claim that this category is equivalent to the category of metrizable topological spaces. Yes, it's clear why, because you have a functor from this category of metric spaces when you don't care about the metrics to metrizable topological spaces. By definition, it's essentially surjective. It's even on the level of objects. And it doesn't change the notion of morphism, so it's fully faithful. So this functor is an equivalence of categories. And obviously metric spaces is a subcategory, not a full one. Say metric spaces with isometries. It's a subcategory, not a full one, of the category of metric spaces when you don't care about the metric. So it means that you basically can think about it as a subcategory of metrizable topological spaces. And of course, metrizable topological spaces is a subcategory of all topological spaces, even a full one. Yeah, and okay, this also relates to something that I said before. If you have structure but you ignore it, from the point of view of category theory, you can assume that this structure does not exist. Yes, so for example, linear spaces with a fixed basis. So if you remember the basis, so you take linear spaces with a fixed basis, but maps are only maps that respect the basis. I don't know, maps the base to basis, one basis to another basis. Then this category becomes more or less a category of sets. But if you have a fixed basis but you ignore it, so linear spaces with fixed basis, but the maps are the same map, then this category is just equivalent to the category of all linear spaces. And this is something very common in category theory. So if you put additional structure but you ignore it, so it doesn't change the category, except of maybe make it smaller full subcategory if the structure doesn't always exist. But if the structure exists, so if you can always choose it if you ignore it in your definition of morphisms. Okay, so maybe I will give some exercises. So yeah, this allows you to replace any rather large category with very small category whose objects are more or less only the isomorphism classes. So let's do exercise. So we have the category of vector spaces. And now let me define, or say finite dimension vector spaces. Let me find this finite category. Let's call it matrices. Objects equal to integers, and more between n and m equal to matrices. n by n matrices. And the multiplication is the composition is just matrix multiplication. So the exercise is to prove that they are equivalent. And in fact, the equivalence is rather canonical. So what do I mean? There is a canonical functor to this direction. The inverse one is not canonical, but it exists. And the proof is very simple. You just do the canonical functor and prove that it's fully faithful and essentially surjective. So on the first glance, it looks weird because this is much larger, but this is what happens when we make equivalence. We can take something large and make it something much smaller. Any questions? No questions? Okay, so let me do some examples of functors. Not necessarily equivalence. So nice general set of example is a forgetful functor. Forgetful functor. So there are many different functors that are called forgetful functors. It's not a mathematically defined notion, but it's clear from the context. So basically, when you have a structure and you forget it, then it is forgetful functor. Also, when you have a condition and you forget it, then it is forgetful functor. So, for example, you have a forgetful functor from vector spaces to sets. Yeah, you forget the fact that it is a vector space and it is a set. No. So you also have functor from vector spaces to abelian groups, because any vector space is first of all an abelian group with some additional structure, so you can forget the additional structure. Now you have forgetful functors from abelian groups to groups. You can forget the fact that they're abelian. Now you're not forgetting a functor structure, you're forgetting a condition. And of course, you can have a forgetful functor from groups to sets, just forget the group structure. And maybe here we have monoids. And yeah, what are monoids and semigroups? Yes. Yeah, so each category have or each reasonable category have a forgetful functor to sets, and maybe not reasonable, but of this class defined by some structure. And you usually have a full hierarchy of structures that you can forget and fact that you can forget. Usually when you forget an axiom like condition, then your forgetful functor going to be fully faithful. And if you forget both condition and a structure, then your forgetful functor going to be faithful. But this is not always the case. So you remember the example of unital rings and rings. You forget the condition of having unity, and you get a forgetful functor which is not fully faithful, because you now allow more morphisms between rings. But maybe the correct reason is that having unity, although you can think of it as a condition, but it's better to think about it as a structure that you fix the unity, and then your maps have to respect this structure. Okay, so somebody want to suggest more examples of functors?
Abelianization.
Abelianization, great. Yeah. Functors from group to abelian groups. You can take a group and force it to be abelian. You quotient out by anything not abelian. There is another way to force it to be abelian, just consider its center. Also, there is a functor from here to here, from monoids to group. You have a monoid and force it to be a group by inverting all the non-invertible elements, which sometimes kill lots of elements, but it still works. This is the way we got the integer numbers from natural numbers. And this is very common. Each time you have a forgetful functor, you often have a functor, one, sometimes even two functors to the other direction. And this is related to something that's called the joint functors, which we'll discuss in a couple of lectures. More examples that somebody want to discuss? Okay, maybe. Yotam, you want to say something?
I mean, there was a lot.
but you can choose what you like.
Fundamental group.
Fundamental group, great. Yeah, so this is functor that does not come from this picture of forgetting something or making something in for. So it can be forced into this picture, but it's not naturally comes from there. So we have functor pi1 from topological spaces. You can maybe restrict it to some nice topological spaces, but that doesn't really matter. Two groups. Okay, whoever know what is a fundamental group, or may in fact point to topological spaces. Point to topological spaces. Two groups. Okay, maybe what?
Maybe it's not the right thing to say, but I just want to say that center of a group, well, it is a functor in the other direction, but it's not one of the two functors that might relate to forgetful.
It's not a joint for any side?
No.
I wasn't sure, but I had some guess that it is, but okay. Okay, so we'll discuss it when we discuss adjoint functors. So another funny example is a dual space from vect to vect, but it doesn't really work, so I won't take any space to the dual space, but it's not a functor according to our definition because it reverse errors. So we put here op, and now it is a functor, the dual space. If we apply the dual space twice, then we get a functor from vector space to vector space, which is often isomorphic to, which is on finite dimensional spaces, isomorphic to the identity functor. But in general, we just have morphism from the identity functor to double dual. Yes, so we have the double dual from vect to vect, and we have natural isomorphism from identity to double dual. Yeah, this is a natural transformation, which is also actually natural as an object. So I know how to, like, it's a isomorphism between two objects, and not just a morphism. And if we restrict ourselves to finite dimensional vector spaces, then this natural morphism become an isomorphism. What else do I have? Okay. The limits and colimits. Maybe before this home. I have, if I have x and y, I have two nice functors that I can associate to this situation. So I have a home from something to y, and home from xa to something. So they're both functors from the category C to sets. Maybe I should write more to be more general. Okay, now I have to be careful. This is from C opposite to sets because it reverse errors, and this is from C to sets. This is from C to sets, but if I'm working in an additive category, then these factors to abelian groups. So sometimes this is each of those factors to abelian groups, and here I have the forgetful functors from abelian groups to sets. And if I'm in some categories, I even have more structures or structure on the home, and the home going to be objects in some other category. So it means that one can define nice functor of home to some other category. And maybe the ultimative case, or in some sense, is when you have an internal home, that some categories have some natural construction of internal home, which give you a functor to the category itself. For example, vector spaces, you take home between two vector spaces, you get a vector space. Okay, so also we talked about the ag, what I'm doing here, ag gamma C, the category of all diagrams of given shape. we talk about category of all diagrams and all commutative diagrams of a given shape. So this is a category. And now we discuss the notion of limit, which for each diagram assign us element in C. So of course, now you see that this assignment is in fact a functor. So the limit is also a functor. And of course, co-limit is also a functor. Okay, I think we're out of time. So any questions before we make a 1 week break? No questions? Okay. So see you in a week. Hopefully next time the internet will work. Alexei, are you here? No, Alexei is not here. So we'll talk to him next time.
Thank you very much.